All right, so for those of you that have had have not had Java experience, or even for those that need a refresher, I would recommend taking a look at the series of videos over the last week in the main section, because we've been going over a demonstration where we developed this book, author, kind of data structures and classes and stuff like that. And so I would highly recommend that you take a look at that. I will, of course, post the code for it. But we went through, making this book class and adding the functionality to get the age of the book. We added this person class to represent an author, tied all that stuff together to finally produce a report that very much looked like the video game report that we did in class in Python, but we did it in Java. So I would encourage you to check that out if you need some more Java experience. Otherwise, the crux of what we covered was that Java is a class-based object-oriented programming language. What that means is that everything in Java is a class or belongs to a class. And that means that classes are the basic building blocks when you solve a problem using an object-oriented programming language like Java. The first question you should ask yourself, beyond has this problem already been solved for me, is what classes do I need to build or to create to represent the real-world entities or ideas that I'm trying to model with this problem. Classes allow you to group multiple pieces of data together into one logical unit, just like we did with video games in Python. We had the title, the platform, the release year, etc. Right? It also allows you to encapsulate methods that act on that data within that class itself. So it's strong encapsulation. The grouping of data, the grouping of functionality that acts on that data. Remember, we are online, so if you have any questions, you can go ahead and post to Piazza. Otherwise, the only comment is I love Nirvana, and I've been playing Incesticide every Friday for the intro music. We're now on week 3, so we're on track 3. Anyway, it allows you to group functionality together with that data that acts on that data, and it also allows you to protect that data. That's something that Python didn't allow us to do. You don't have this private keyword in Python. Instead, you have conventions that attempt to send a signal to you not to touch this stuff. So our first demonstration here is going to be basically a truncated version of that book demonstration, but on this isotope problem that we were facing the other day, where this is my translation to Java of the same problem that we solved on Wednesday. Where we're given a radioactive isotope with an atomic number, an element name, element symbol, a half-life in years, and then an initial mass. And then it produces this decay table that after so many years, starting with this amount, we have so much left over, and then with the decay products, right? Because mass is neither created nor destroyed, just like energy, and it just changes, right? It changes into uridium or whatever it is. So let me go ahead and show you that this actually does work. Run it once, and we expect command line arguments, run configurations, arguments over here, strontium, what were the arguments? Let's see, oops, head up here. Atomic number, what is strontium? Anybody help me? 38, wasn't it? Yes, no? Oh, well, it was strontium 90 that we wanted, so, but the atomic number is 38. The element is strontium 90 was the isotope that we were playing around with, and then it's SR, and then the half-life was 28.9 years, I believe, and the initial mass was like 10 grams or 10 kilograms or something. Right? Apply that, run it, and there's the same exact table that we produced in Python on Wednesday, but it's being produced in Java here. Right? It was just a direct translation. If you're interested, first of all, the standard going forward for Java is going to be that all classes need documentation. So let me put that in. Like all good programmers, I don't want to do it, so to do. Right? Any non-trivial functions require documentation. To do. Right? Main is a trivial function. Main is a trivial method that does not need documentation. If you want to put documentation, go ahead. Right? If you want to write a note to yourself or whatever, go ahead, but you don't need it. Right? Otherwise, we're going to check our arguments here. And by the way, it is nicely formatted already because I just did a Shift Command F. Right? And then I got it in the standard format. If we don't have 5 command line arguments, the atomic number, name, symbol, half-life, and initial mass, then we print out to the standard error here that I expected 5 arguments, and we exit on them. Okay? Otherwise, I read command line arguments here. The first one is at 0. Remember that in Java, we don't need the name of the executable file because it's right there, Isotope demo. Right? So the first one is actually the user-provided argument here. We convert that to an integer because all atomic numbers are integers. 1, hydrogen, 2, helium, et cetera, et cetera. Otherwise, we don't need to convert the element name or symbol here. These are the first argument and the second argument and the third argument respectively because they're already strings. But I am giving them more descriptive names. Element name versus args1, right? There's a clear winner there. There's a clear better name. Then I've got the half-life in years. That's a double parse double. We start out with an initial mass here. I'll keep my counter as a year here. We print out this header. This is something that might be new to a couple of you. What is this thing right here? 3 double quotes. I think we covered this in Python, didn't we? Yeah. What is it? It's a multi-line string. Leading white space here will be ignored so that you can go ahead and just put this into one big giant string and not have to worry about the formatting. You don't have to insert end-line characters, etc. You can get it to look as nice as you want without having to write multiple lines to do it all. Right? And that's what it looks like here. Right? So there's the first line, and then here's the next header line right here. Otherwise, while the mass is greater than or equal to 1/2 of the initial mass, we will print out the year and the mass that we have, increment the year, and then call this decay function here. That whatever mass we have, we're going to decay it by 1 year given this half-life. Right? So there's the formula. Year divided by half-life, 0.5 raised to that value, times whatever mass is, and we return that value. Right? So the mass is going to go down as we go along here. I only decay it by 1 year at a time. If you wanted to decay it by, say, a month at a time, or what would it be? 0.125, right? 125 years is what I'm doing. By the way, what about that? What's happening there? I had to help somebody with this in an upper level course the other day. Something wasn't working, and we tried 5 different things because it was an upper level class, so I was figuring it was upper level problem, but it was this problem. 1 divided by 12 is what? 0, because of integer truncation. And that's why we're never decaying, because we're decaying it by 0 years, 0 years, 0 years. Right? Don't do that. Right? In Python, you can do that. 1 divided by 12 will be, it's not 1.25. What is it? 0.0833333 or something? Yes? Anyway, who cares? It's just 1 year. All right. So now that we understand this problem, let's observe how I wrote this thing. I wrote this in a what's called procedural style. When you say a procedure, you have a list of things to do. Task 1, task 2, task 3, task 4. Oh, well, I'm going to go ahead and offload that task to this method over here, this function over here that takes care of some of the details for me. And then that'll also offload some of the details of the mathematics for me in turn. But it's still procedural. You've got task, task, task. You call function, but then you return task, task, task. That function does task, task, task. There's no object here at all. Right? So what I want to do is I want to take an object-oriented programming approach to this. My first step will be to identify something that will model a or an isotope. Right? An isotope class. Now, forget about the behavior for now. Tell me, what is an isotope, at least as far as this problem is concerned? It's these 4, 5 things. Right. Okay, let's bring that over. Let's modify it. Right. First of all, I'm going to make them all private. Right. That, can't see it now. There we go. Right. And I don't have command line arguments here. So I'll go ahead and get rid of all that, get rid of that. There we go. I'm just doing this to save on typing. Stealing that other code there. And not initial mass, but I'll just call this mass. Okay. I've got myself a really good start of a class. In fact, most of the amazing things that I've seen people claim that ChatGPT does is basically what an IDE does, right? It generates, you tell it, I want a class that represents an isotope, and I want an atomic number, and I want an element name, and a symbol, and a half-life, and a mass. It says, okay, and it produces something like this, and then it'll go the extra mile, and ooh, wow, cool. It'll produce getters and setters. It'll produce a toString method. It'll produce constructor using fields, which is what I want here. Right? Generate that. Oh, and it puts it up there. I don't want it up there. I want it down here. There. Reformat. So it's not AI. It's just simple code generation, right? And this stuff is all over the industry. Later on, when we get into your actual project, you'll be required to create a UML diagram. Come on. There we go. Done. It automatically did it. By the way, you can go backwards too. You can create this is universal modeling language. You can create a diagram of your classes, and then it'll just spit this out up here. Right? Auto code generation. It's nothing special. Okay? Let's get rid of that because I don't want to focus on it. We'll come back to, I don't want to focus on my problems either. There we go, console. All right, so there we've got our first class here and a way to create that class. So I'm going to come over here and change, well, no, I actually want to keep this separate. And what I want is a new class to demonstrate this demo. All right? Because when I eventually post this, I don't want to muck with this code. I want you to see the difference, the stark difference between a procedural style and a object-oriented programming style. Public static void main string args. There we go. So now that I've got that class, I can actually create instances of that class. So isotope, right? Strontium sample A, right? I can create a new isotope of what was it? 38 strontium 90. Am I spelling that correct? Anybody? It has a half-life of 28.9 years. And here's my first sample. It has 10 grams, 10 kilograms, 10 pounds. Right? Is that defined over here? It's just mass. Right? Even if you restrict yourself to the proper metric, it could be grams, it could be kilograms. There's some programming languages out there that have what's called strong typing, where you would say that this is not just a double, but it's a private kilogram, right? Mass. And then later on, what you could do is you could say that if I've got, let me go ahead and undo that. There we go. You can do something like this in some other programming languages. Like you could say that kilogram mass A is equal to 4. And then you could say a pound of mass B is equal to 5. Now you could say result. So kilogram result is equal to mass A plus mass B. And it looks kind of cool to begin with that it would automatically convert that pound into kilograms so that it would give you kilograms as a result and properly do everything for you, right? However, then you realize, why am I even talking about pounds? I'm a proper computer scientist, which means I'm a proper scientist, which means that we're not in that, we should not be in that arena, right? So the use cases are actually quite limited for strong typing in some programming languages. There are going to be their advocates out there that will scream at me if they happen upon this random internet channel or this random YouTube channel, but so be it. They're screaming in the wind, right? All right, so there's sample A. Here's sample B. That's only going to be 5 kilograms. And I'll rename this B. There we go. And I could, produce a decay for both of these separately. What if I don't have a sample? What if I just have the idea of strontium? Right? In other words, I want a way to represent the idea of strontium, that it has atomic number 38, it has this name, symbol, and a half-life. But I don't really have a sample of it. One way that I could do that is 0, right? I have a 0 kilogram sample in my hand. That's not all that satisfying, though. Right? So what I want is, let's come over here to the isotope class, and let's extend some functionality. What if you want to create an instance of this class, but you don't want to give it a mass? Nothing stops you from creating multiple constructors just without the mass. There. Now over here in the demo class, you don't have to give it this flag value of 0 to indicate that it is a sampleless idea of strontium. In fact, I'm going to not call that idea of strontium anymore. I'm just going to call it strontium. All right? Am I pronouncing it right too? I have no idea. Somebody look that up for me. I don't know. All right. Anyway. Okay, so I've got 2 constructors here. One of them that takes all 5 input pieces of data, one of them that only takes 4. But you know what? I hate repeated code. The DRY principle, don't repeat yourself. How can we improve this? How do we have some repeated code here? That's repeated with that right there. Right? So my first step here is to eliminate one of these, or blocks of lines of code, these 4 lines of code somewhere. If you were doing this in a function, because these are functions, first of all, determine which one of these functions is more general. The one with 5 or the one with 4? Which one's more general? What, oh, I'd say 5. Why? Because it depends on your perspective, I guess. I'm going to call it the one with 5 because it takes more stuff. That's my criteria for general. All right. So in other words, I want this this constructor to call that constructor, right? So I'm going to pass in atomic number, element name, element symbol, and half-life. If I spell everything correct. Symbol, there you go. Except that it also expects a mass. So I'll just go ahead and say, I don't have any mass to give you, so I'll say null. Ooh. Can I do that, though? Let's find out. Hold on to that thought, first of all. How do I call that function? What's the name of that function? Isotope. So my first attempt is going to be isotope. Isotope. That doesn't work, though. Right? That's not the syntax. Well, I knew? Nope. All right, so how does how does an object in Python refer to itself? How did we refer to ourselves in Python, a video game? How do we, self, right? That's kind of anthropomorphizing it though, right? It's me, myself, I. It's not a person, it's an object. So how are we referring to this? This keyword. And likewise, any constructor is going to be called this, okay? Now it's not letting me do this because it says null. Nope, lowercase d double cannot be null. All right, maybe now I have a reason to refactor this and make this into an uppercase D double so that you can have a massless idea of an isotope like strontium. Okay? All right. No repeated code here at all. What else did I want to do? Oh, I wanted to draw your attention to the importance of this keyword. Without it, what does it mean? How many variables right now on line 12 are there called atomic number? There's certainly the parameter. Is that the only variable called atomic number? Nope, there's one right there. So what is this line doing? This would be like doing something like the following. Int x is equal to 42. X is equal to x. Should line 14 exist? No. Should line 12 exist? No, because that's what you're doing. All you're doing is taking this parameter variable and putting it back into the parameter variable. That's why the this keyword is necessary. Even in situations where the this keyword is not necessary, you should still have a good habit of putting that in there. Okay? Let's get back up here to private, because we have seen this before, I think. We live now in a Python world where there's no privacy at all. Over here in demo, oops, what's wrong? Oh, no, what? Why are you complaining? Constructor in double is undefined. Oh, that's because, fine, it's being really pedantic about it. Right. 10 is not 10.0, right? It needed an actual double there. All right, so, all right, back to the drawing board. Strontium, dot, did I make mass? There we go. There, mass 7.5, right? This is what happens in Python, where you don't have strong encapsulation. And when you create an object, you can go ahead and do whatever you want with it. That's why it's called duck typing. If it walks like a duck, talks like a duck, then it's a duck. If it has a mass, if it has an element name, if it has the rest of the stuff, an atomic number, then it must be an isotope. But we don't live in the Python world. We have strong encapsulation. We have the protection of that data, right? By making this private, then you can't do something like this. And that's preferred. All right, let's come back over here. And, well, sometimes you do want to get the mass, right? Because, for example, I want to get the mass so that I can decay it by a certain amount and then update the mass. Okay. Well, if you want to do that, then let's go ahead and go up to source, getters and setters, and I'm just going to go ahead and select all. There we go. And generate. There we go. What that does is for every member variable, it creates a getter function that allows you access to that variable value. But unfortunately, in my zealousness to generate this code, I also selected all the setters. So now over here in the demo, I can do the same thing just in a different way. Strontium.set mass, set mass to be 7.5. Right? That seems in a way to not be a good idea. Right? If I've got a sample of 10 here and a sample of 5, right, I want that to decay naturally according to the process. I don't want somebody to just go willy-nilly and change it, right, arbitrarily. So what I'm going to do is I'm going to come back over here to the isotope class, and as another even stronger encapsulation step, I'm going to make all of these final. Okay? Those of you coming from a C background will recognize this, final. It's, if I said const instead, right, then you would know that this is a constant. It's no longer a variable. Once it's set, you cannot change it anymore. There is a const keyword in Java, but it doesn't do anything. It's just a reserved word. They thought that might as well reserve it because C has it. We'll think of a use of it later, and they never did. Right? So you can't use it as a variable name. You can't say int const, right? Int const is equal to 42 because it's a reserved word, and you can see that it's in magenta right here. Right? But it doesn't do anything. Right? These are all final now. Guess what? All my setters now do not work. Why? Because once it's set, you cannot change it. I like that, right? And you should like that too, because that means that my isotope class here, undo, is now immutable. Get half-life should work. Come on, there we go. Reformat, there. Get rid of that, get rid of that, and there. We're all good now again. Right? It makes my class immutable. No, you cannot set the mass. Right? If you want a new sample that is 7.5 kilograms, make one. Right? Okay, fine. Sample C that is 7.5 instead. Okay? Except that, remember that DRY principle? That's still getting to me here. Don't repeat yourself. 38, strontium 90s, SR, 28.9. 28, repeated now 4 times, right? Okay, there's got to be a better way. There's got to be a way that if I've got a sample of strontium or the idea of strontium, that I can create another sample, and another sample, right? Let me come over here and show you another constructor, right? Public isotope, right? isotope sample. I'll call it isotope. There we go. So I'm not taking the atomic number, the element name, element symbol, etc. What I'm taking is another isotope here. Right? You've seen this before probably if you've done Java. Right? So let me go ahead and create a list of integers, right? Numbers, right? Is equal to new array list. Right? There we go. And I'll go ahead and go numbers.add 10, 20, 30, and 40. All right, and system.out.println numbers. All right, there we go. Import that. And now I'm going to create another list of integers called b. And I'm going to set it equal to numbers. Then I'm going to say b.add 42. Can't spell today. Now, let's print out the original, and let's print out b. Predict. Is adding 42 going to affect numbers or not? Yes. Why? What am I doing on line 20 here? I've got b. Here's numbers, right, in my left-hand pointer, a reference, right? And I'm saying now I've got b, and what am I doing? I'm making it point to the same thing. We call this a kind of copy. What kind of copy is this? Shallow copy. Right? That's bad. Right? So instead, let's do what's the opposite? Deep copy. How? By saying, let's go with C now. A list of integers called C, and what I'm going to do is that in that parentheses there, that's my constructor. I'm going to pass in B. It's going to copy that list into this list. That's the same pattern as over here. It's going to copy that isotope into this isotope. Okay? And so that changes to one don't reflect on the other. Right? That's just a quick review there. Right? If you want a review of that, I don't have a Java video on deep or shallow copies other than the lecture videos. Right? All right, so I want to copy that isotope into this isotope. So this dot atomic number is equal to that dot atomic number, right? This dot, right? So the code generation is not good enough that it has a copy constructor in it, right? Let's document this first of all. A copy constructor that copies the given isotope into this isotope. There we go. This is a copy constructor. It's halfway between trivial and non-trivial, so please put some documentation in there. All you have to do is call it that, right? It's a copy constructor. Except again, I don't want to type. This, that dot atomic number, that dot, what's the order? Element name, that dot element symbol, that dot half-life, that dot mass. There we go. Done. Right. I'm copying this isotope, or that isotope into this isotope. Now, that was for demonstration purposes. This is a good keyword because it's built into the language and we can't change it, good or bad or ugly. It is what it is. But is that a good variable name? Probably not. What I had originally is better. Here's another Eclipse trick. Refactor, rename, isotope. Not only does it change it every instance in the entire scope, but it also changed my own documentation on me. Right? Really nice, convenient trick. Right? There, done. Now over here, what I can do is, instead of creating a new isotope with 38 strontium-90 SR 28.9 repeated over and over and over again, I can take the idea of strontium and pass it into here. What did I lose, though? That 10 grams, kilograms, or whatever. Right? A copy constructor doesn't have to be a pure copy constructor. It doesn't have to purely copy that thing over into this thing. You could have a copy constructor that looks like this instead. Let me copy just this part. There we go. It takes an isotope, yes, but it also takes a mass. I'm going to go ahead and copy over the 4 things that I want to copy over. Atomic number, element name, we screwed up already. Element symbol it should be. There we go, and there we go. The half-life, but I'm not going to copy over the isotope's mass. I'm going to override that with the mass that you give me. Now I've got the best of all worlds. That sample is a sample of strontium, and it's 10 grams. That sample is a sample that's 5 grams, a copy of a sample, a copy of a sample, copy of a sample. Right? This is a really nice pattern to follow. Right? And what does it look like for documentation? A copy constructor that copies the given isotope except for the mass. And let's code it, mass. Surrounding it with a code tag means that when you look at the documentation here, that's in monotype font. It's kind of difficult to see, but it looks like code when you actually, publish it. This is actually just HTML. You can do this in HTML as well. And it'll show up like a monotype font. Right? Okay. All right. Excellent. That's a good data model. Let's not lose the forest for the trees, though. We still want to produce this decay table right here. Okay? So, all right. Let's go ahead and copy this stuff over. Let's see. No. Let's just go with one of the samples over here. Over here in the demo. Right? So, actually, what I do want to copy over is this thing right here. There we go. To do. And bring this over here. And let's just go ahead and decay sample A here. I'll leave these as just demonstration here. So let's produce a decay table for sample A. Okay. For that, I'm just going to go ahead and take this code right here. Right? And, I do need an initial mass, I guess. There we go. And bring this over to demo there. So how are we going to have to change this, first of all, if I'm working off of sample A here? Well, to get the actual mass, it would be sample A dot get mass. There we go. To print out the element name, the atomic number, the element symbol, I would have to go sample A dot get element name dot get atomic number dot. Right? Is there a better way? If you want to print out information about an isotope, it acts on the data, right? It acts or operates on the class's data. Where should it belong? So I've got a piece of functionality that formats an isotope's information and prints it out to the standard output. Where should that logic belong? It operates on an isotope, so therefore it belongs in the isotope class. That's called a toString method. Right. There we go. Now, the code generation here is kind of crappy, but it's a good starting point, string.format. There we go. That's basically an sprintf implementation. And so I'll go ahead and format it. How do we want to format it? Let's steal this formatting. There we go. Isotope. There. Done. Right. And now over here in the demo, I don't rip those things out. Instead, I have a toString method that does it for me. Right. Simplify. Now, overall, the numbers of lines of code, the number of characters of code is the same, but there's less code here to have to think about. Right? Just like you wouldn't have a God function, right? You wouldn't put everything into main, would you? Right? No. So you wouldn't put everything into one class either. You would put stuff where it belongs. This isotope stuff over here belongs in the isotope class. That book stuff belongs in the book class. that person stuff for an author belongs in the person class, right? And you don't mix them up, right? You want a separation so that you have code reuse. That takes care of that. There's my header, as usual. And then initial mass. Okay, initial mass is what? strongtm.getMass. There we go. And then the half-life is strongtm sample A dot get half-life. There we go. Fixed, 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 fixed. All right, let's see if that works. It produces the same table. But it's kind of icky still. Why is it icky? Let's focus on this function right here, decay. Right? What is it doing? It's taking a mass, it's taking a number of years that you want to decay it, and it's taking the half-life of the sample, right? Or the mass of the sample as well, right? So in other words, this is functionality. Again, it's a method that acts or operates on the class's data. What I'm doing right now is I'm breaking encapsulation. I am going to the class and I'm ripping it open and I'm saying, give me the mass, give me the half-life, so that I can hand this off to a third party. They can do some math. I will take those back and then I will reset your mass, right? With a setter or something like that, right? That doesn't sound right, does it? Stuff that acts on the data, stuff that acts on an isotope's data, like half-life and mass, should belong in the isotope class. So let's take this decay method and move it, right, into the isotope class. Right? Now let's document what it does. Oh, first of all, do I need to take these as inputs anymore? Mass? Nope. Why? It's this isotope's mass. Do I have to worry about bringing in a half-life anymore? Nope. It's this element's isotope's half-life, right? This dot. Oh, and by the way, I need to take away static now, because it no longer belongs to the class. It belongs to instances of the class. Here's sample A, here's sample B, here's sample C. If I decay this one over here, I don't want that to affect this one over here, right? And so everybody has their own mass. Everybody has their own decay instance, or decay behavior, okay? So let's take away the mass, leave the year because we need that as input, and then there we go, right? So decays this radioactive isotope's mass by an appropriate amount given the decay period in years. Right. There, it changes it, okay? So instead of returning a result here though, I'm going to decay my own mass. This dot mass is equal to result, right? I am changing my mass, right? Well, wait a second, I thought we couldn't do that. Why can't we do that? Because I chose to make it final. Generally, you should make everything private and final until you have a very good reason to do otherwise. Those are all those are capital letters there. We now have a very good reason to do otherwise, don't we? Because we want to decay it. Right? All right, fine. Go ahead and open it up. Right? You should be as conservative as possible on your design until you have a use case that you need to make it more flexible, right? That you need to open it up a little bit. Right? All of these should be private until you have a very, and this way it's going to be two V's here, a very, very good reason to make it public. Right? For example, the math library, right? Public, final, double, pi is equal to 3.14159. We want you to, use that variable. But we're going to make it final so you can't change it, right? That's a very good reason that you would want to do that. But here, we don't have that reason yet, okay? Maybe we will in the future, in which case we can come back and open it up a little bit better. This goes into what are called the solid principles. Single responsibility principle, Interface segregation, or solid, O. Open closed principle, it should be open to extension, closed to changes, or something. L, Liskov substitution principle. I is interface segregation, and D is dependency inversion. We'll talk about those much later after we go through the 4 columns of object-oriented programming. Right? But one of them we can see now, right? The single responsibility principle. What is an isotope? It's an isotope and it has these 4 things and this behavior. Right? Should I be putting book stuff in this class? Nope. Should I be putting, say I wanted to process a file that contained a bunch of isotope information. Should I put that in this class? Nope, that sounds like a data loading stuff. It probably belongs in its own class. Right? Separation of concerns, single responsibility. Right? Well, decaying, that sounds like it's operating on a year and an isotope. Yeah, but it's more closely related to an isotope, so that's not violating that principle to put it in here. There is a huge white area where it is clearly correct to do this. There is a huge black area where it is clearly not okay to put things into other classes. There is a giant gray area in between that you can debate about. Right? White stuff, white area over here, absolutely do it. Black area, oh, do not do it. Gray stuff, that's where you team up with a partner and you start whiteboarding stuff. And you go back and forth. Well, what are the advantages? What are the disadvantages? Right? Well, let's go ahead and put that into the white area until we have a reason to do otherwise, and then pull it over here. Design, redesign, reiterate, refactor. Right? It's all part of the process. Okay. Now come back over here, and let's change this. So I don't have an initial, where's my initial mass? I don't need this anymore. Right? I do need that because it's a counter. And I do need an initial mass is what I wanted. Double original mass is equal to strong TM sample A dot get mass. There we go. There's the original mass, while it's still at least 1/2 of the original mass. Now it's a strong TM sample A dot get mass. There we go. Strong TM sample A's mass is equal to a decay of 1 year. There we go. And mass, just to print it out. Right? Oops, can I do that? Well, that's a function that returns something. Can I go 42 is equal to 3 or 2? No. Syntactically, that doesn't make any sense either. But what's decaying? Strong TM sample A is decaying. I'm sending, this is called message sending, right? This is how object-oriented programming works. There's this object here called strong TM sample A. I am sending a message to it to decay itself by 1 year, right? 1 year's time. And it takes care of all those details for me. I'll do that. I'll compute the result and then set my mass equal to the result and then return back over here to demo. Right? It looks like I'm calling a function, and at the end of the day, that is what I'm doing. But it is much, much deeper, right? Philosophically, as far as programming language paradigms go, right? I am sending a message to this object to do something. And it's receiving that message, and it's doing the thing that I told it to do. Okay? Let's see if this still works. Make sure that it still works. There we go. It does. But it's much cleaner code, right? I don't have to worry about this anymore, do I? Right? I don't have to worry about the details. Why? Because it's in the class. One last improvement I want to make here is, here, let's come back over here. If you don't look at the documentation, if you don't look at the class, do you know what 1 is? 1 what? 1 year? 1 second? 1 day? What is it? If you don't look at the documentation. Mysterious, right? So I want to improve that by improving the modeling, right? So we did this with the book class, and I won't go over the details here, but we started out by representing a book with a author first name and last name as strings. Does that sound right? Should I separate those two things out? Anytime that I have more than one piece of data, what should I be doing to it? Making a class, right? So we made a person class to represent an author. And then we thought, well, we want to make it so that they have a date of birth, right? So integer year, integer month, integer day. 3 things. What should that be screaming out to you? Make a class. Or use a built-in class, and there is a built-in class for that. It's called local date. Right? That represents an instance in time, right? Today is February 10th, 2023. That's not what we have here, though, right? What we have here is a duration of time. Duration. D, right? That's built into the language, too. What's the difference between a local date and a duration? Well, a local date is one instance in time, and then a duration is like a month or a year or a second or something like that, right? And so that's what we'll take here. D dot get days, is it? Get, not units. I'm going to have to remind myself just a second here. I forget how to do it, sorry. 2 days, there we go. Dot 2 days. There is not 2 years, it's more precise than that. But what I can do then is divide that by 365, right? 2 days is going to be an integer, or it's a long. Long divided by an integer is still going to be an integer, so what should I do? Make one of them at least a double, right? That gives me the number of years. Mathematically, am I okay? I don't know. So I'm just going to go ahead and be safe and put it into parentheses there, right? Now, here's a good question. Is a year actually 365 days? Not in scientific terms. It's 365.25, right? There we go. One of our faculty had a birthday on February 28th, and so it made me highly suspicious that he might be a leap year baby, right? Leap year baby is born on February 29th, right? So I need to check with him to see if he was actually born on 29th and then just celebrates it on the 28th, right? Anyway, there we go. So same exact behavior here, but I want my duration here. Duration year is equal to duration dot of, there we go, of hours, days, let's just go with days here, 365, there we go. And then I can put in year here, year duration, because I've got 2 years duration, there. And now it works if you want to do it by a year, if you want to do it by 31 days instead, right? Isn't that cool? Right? I didn't have to worry about, oh, okay, well, I'll have a different counter here. It still goes down to 4.99 grams, but it took 341 periods of 31 days. What if it was just 1 day, right? 28.9 years is going to be 10,556 days, right? But I'm able to talk about those things because I've modeled it correctly, right? We don't have the luxury of saying that this mass is kilograms and that mass is pounds, but at least we do have a correct model of duration built into the language, or at least into a standard library, okay? So your takeaways on this is when you design a class, you make sure that you have the correct model. You can go too far. That gets into the Yagni principle. Yagni, right? So creating a person class to represent a person, good, right? Creating a name class to represent a person's name. This is one of the most common mistake we see. That's over-engineering. That's Yagni. Does anybody remember what Yagni stands for? You ain't gonna need it. There. That's over-engineering. That's the Yagni principle. Creating a person class, good. Creating a name class that contains a first name and a last name, what? Why? Overly complicated. Creating your own date class or duration class. Good idea, bad idea? Bad idea. Why? It's built into the language already. Do not reinvent the wheel. Do not roll your own unless you have a, and I've erased it now, I should have kept it in a comment, very good reason to do so. Right? Use what's there. All right. Good luck on your homework. Remember, you have until midnight. The final office hour, help hour, though, is at 4:30. It goes until 4:30. Right?